right, everyone, should we get started? Okay, so welcome to the session on AutoML for natural language processing. I'm very happy that you're here. So my name is Kevin Du. I'm a faculty at the Johns Hopkins University in Baltimore, US. And my main research is in machine translation, but throughout work on training these machine translation models, I've sort of found a need to do AutoML. And that's why I'm presenting this here. And my co-presenter is Zhang. And do you want to introduce yourself a bit?
Okay. Hello, this is Xuan. I'm a fourth-year PhD student at Johns Hopkins University, and Kevin is my advisor. I work on hyperparameter optimization, machine translation, and side language processing. I really want to be there in person, but anyway, this is challenging for both the audience and the speaker. I'm hoping I won't talk you to sleep, but if you do fall asleep, what can I say? Have a good sleep.
All right.
Anyway, I hope this tutorial is helpful to you.
Okay, great. Okay, so before we get started, this is our website. It's very simple. It just contains the slides. So in case you want it, you can take a picture of the QR code in case you want to have the slides. Okay. You can also find these slides on my webpage. If you just search for my name, you'll find it. Okay. All right, so let's get started. Before I begin, may I ask how many of you here have worked on AutoML or heard of AutoML before? Okay, a few of you. So I'll try to make this interactive, and we can go as fast as you want, as slow as you want. It is really up to you. We're a small group here, so we can really make it geared towards what you want. Okay, and if you want to go out to enjoy the views, we can also end early. I'm totally happy with that. Okay, so AutoML for NLP. Let me begin by a sort of motivational question or observation. And that's something pretty obvious. It's very important to tune hyperparameters. I'm sure you've all done this in your research, trying different hyperparameters and seeing different results. So here, I'm going to illustrate in the machine translation example. I trained about 700 different transformer models using different hyperparameters, like different layers, different embedding sizes, different learning rates, different BP units. So basically just kind of brute force grid search. I trained this on a relatively small data set, Swahili English. And so here, this is a histogram of the BLEU scores. So as you can see, most models on average, we have about a BLEU score of 20. And a few models get a very good score of 25. But actually a big portion of the models, a big portion of the models have very low BLEU scores. And actually the statistical MGCs is around here, 23, 24. So this is an illustration saying that we might get a lot of good results with our models, but that's because we got good hyperparameters. If you were unlucky and you didn't get a good hyperparameter, you might be in this range, right? I'm sure you've all kind of experienced that before. Okay, so that's sort of what got me into this field, is realizing that, hey, hyperparameters are important. It's kind of annoying, but it's important. All right, so here are some example hyperparameters I'll be talking about. So as you see here in this figure, that's the transformer model. I kind of divide hyperparameters into different types. So one are architectural hyperparameters. This relates to how the network is shaped. So things like number of layers, number of hidden units, that's an architectural hyperparameter. There are also training pipeline kind of hyperparameters. So number of subword units, right? So that's kind of pre-processing. How do you want to do that? There's also optimizer hyperparameters. And these are things that affect your optimization process. So like what optimizer to use, what's the learning rate, what regularizer do you use? Those don't affect the actual architecture, but they affect your final results. They affect your training speed as well. Okay, so those are sort of the three things I think about. I think hyperparameters, architecture, training pipeline, and optimizer hyperparameters. Okay, so then now we can ask the question, when we talk about AutoML, what do we actually mean, right? We're talking about trying to automatically optimize these hyperparameters. That's one way to view it. Now, it actually means different things to different people. And this is sort of a buzzword in a sense. So for consumers, AutoML means democratization of ML, right? And a lot of companies are offering their services with the label AutoML in this sense. So basically, users can upload their own data. Oh, I realized there was some echo. Sorry about that. So users can upload their own data, and then the service will train a model with the right hyperparameters, and then give you back the best possible model, right? So that's one kind of AutoML, basically making it easy for anyone who's not an expert in machine learning to field their systems. Now, for developers, AutoML can mean that you reduce your effort, right? So that can automate a part of my model building pipeline, which means I have more time to do other stuff. And this is especially important, and we'll come back to this later, for developers who need to care about speed accuracy trade-offs or size accuracy trade-offs, these practical deployment trade-offs. Those are really hard to get right, and AutoML can help you do that. Now in this case, my case, NMT researchers, but generally for NLP researchers, this AutoML can help you obtain state-of-the-art results, right? So say I have a new idea, I want to try it on this data set. I also have a baseline I want to try on this data set. It's best if we run the same hyperparameter optimization procedure for both, then it's a fair comparison. And we tend to work really hard, manually tuning our own method, and then don't have enough time for the baseline method. But if we have an AutoML tool, that will make it easier to do it in a fair fashion. Okay. And then finally, AutoML for some machine learning researchers means something like a holy grail. Right? They want to discover the next transformer architecture. Right? It's kind of interesting that we had these RNNs and then transformers, and then nothing came afterwards, really, right? So there are some ML researchers out there who are really trying, using automated machine learning methods to find the newest, fanciest architecture. Okay, so in this talk, I'm mainly going to focus on scenarios that help developers and NLP researchers. So basically, helping you reduce the effort in deploying your system and training fair baselines. So that's our main focus. And we're not really going to cover the other use cases that much because they're really different. Okay. And I think this happened because AutoML is kind of a buzz term. Everyone's calling their own thing AutoML. Okay. Are there any questions so far? Feel free to raise your hand. And if you're online, feel free to also put something in the chat, or one of us presenters will be monitoring the chat. So feel free to drop any questions or comments you want. Okay. Okay. So recently there was an AutoML conference. This was the first ever AutoML conference last year, happened in Baltimore right after ICML. And these are sort of the topics that people were really interested about. So hyperparameter optimization, neural architecture search, meta learning, auto reinforcement learning, algorithm selection, and systems for machine learning. And in this talk, I'm mainly going to focus on hyperparameter optimization and neural architecture search, since these are the two main areas that may be broadly applicable to NLP researchers. The other ones I would leave out. Although they're very interesting. For example, algorithm selection, there's a lot of work on, say you want to solve an NP hard problem. What kind of algorithm? There are many different heuristics, so there are a lot of work on that. Okay, So basically AutoML, I'm going to use this as an umbrella term to cover multiple things. Sometimes I'm going to say hyperparameter optimization. Sometimes I'll say neural architecture search. I'm kind of using these kind of interchangeably. All right, so the goal of today's tutorial is first to motivate the importance of hyperparameters in architecture search, and then we'll focus on a few popular methods. So I won't be very comprehensive. We'll pick up a few important techniques and explain them to make sure you kind of understand the general idea. Then you can go off and read papers on your own. We'll also do a case study saying if you want to apply AutoML to your own work, right? Say you're doing, say, summarization, and you just want to apply AutoML to it. What are the options for you? You can borrow a toolkit or you can implement your own, and we'll describe our experience in doing that. Okay, and my hope is one day AutoML will be part of your toolbox. Maybe it's already part of your toolbox, but that's sort of, I can kind of see this happening in the near future. Like nowadays, we all use PyTorch, right? We basically have these auto differentiation toolboxes, right? We never need to do CUDA code. But probably maybe in the future, we all have AutoML, like you import AutoML, import PyTorch, and then that's sort of how we do things. Okay, so any questions, comments, anything online? Okay, so here's a roadmap. I've already talked about the motivation. Next, Xuan will talk about the hyperparameter optimization, the major techniques there, and then I'll follow later by talking about neural architecture search methods. And these are sort of the two main areas we'll cover. So basically, it's going to be a machine learning lecture. And probably around that time, we'll have a coffee break. So coffee break is local time 3:45 to 4:15. So I make sure to leave time. And if I forget, please someone remind me, coffee is here. Let's try to get out before the other people so we can get coffee. Okay, so coffee break is 30 minutes. And after that, we'll try to complete the remaining sections. So we'll talk about, so the first part is about machine learning, but the second part is more about how do we apply it to NLP. So what if you want to extend it to multiple objectives, or how do you evaluate these methods in NLP? Okay. All right, so with that, let's get started. Jen, let's switch screens so that you can share.
Mm-hmm. Does it work?
Yeah, we can hear you fine, and we can
Okay.
see. Yep.
Cool. In this section, we'll talk about what's actually is hyperparameter optimization, and we'll go over some representative methods of HPO, and then conclude this section with some generalizations. This section takes about 1 hour. Okay. In hyperparameter optimization, or HPO for short, we're not too concerned with how a model is trained. We won't dive into the model parameters. Instead, we just focus on the hyperparameters and how they would impact the model performance. Take deep learning models, for instance. We might want to do hyperparameters like the number of layers, the number of units per layer, the optimizer type, and the learning rates. Our goal is to find the best configurations for these hyperparameters with as few model evaluations as possible. And we've all been through this in practice. We pick values for hyperparameters, train models with those settings, and then get evaluations, right? It could be accuracy, WER, or BLEU score. After that, we adjust hyperparameters and train the model again, hoping for better evaluation results. And to select hyperparameters, we often use default values or rely on heuristic rules. It's a very tiresome process, and there's no guarantee it will pay off. So is there a way to do better than this? Or can we avoid this tedious process of manual tuning? So it turns out we can actually replace ourselves or any very graduate students with more reliable machines or algorithms in the loop. That happy, smart-looking robot in the picture saves us from the tedious work of manual tuning, all thanks to its HPO algorithm. So HPO takes hyperparameters and evaluation results as inputs and suggests new hyperparameter configurations. The goal is to find the optimal hyperparameters with fewer searches. And in the following of this session, we'll survey some representative HPO algorithms, including grid search, random search, evolution-based search, population-based training, and hyperbands. Okay, let's embark on our journey into HPO, beginning with sequential model-based optimization. This framework encompasses a variety of HPO algorithms, including the widely used and renowned Bayesian optimization. We begin with this hyperparameter search space. So in this figure, as various X, for instance, X1 might represent hyperparameters of 2 layers with a learning rate of 0.5, while X2 might represent 4 layers with a learning rate of 0.1. Okay, after selecting a configuration, say XP here, we evaluate it using our model F. And F could be any machine learning model, and Fx corresponds to the evaluation result. Okay, SMBO, a sequential model-based optimization, has 2 important components: the acquisition function and the surrogate model. The acquisition function's role is to propose the most promising configuration candidates. Meanwhile, the surrogate model approximates the model F. If F is a machine transition model, for example, the surrogate model would take hyperparameter configurations as inputs and output predicted blue scores. And the surrogate model is generally much cheaper to evaluate compared to model F. And SMBO works iteratively. It starts with querying model F with random hyperparameter configurations. And then the surrogate model fits all evaluated points and generates predictions for all other configurations in the search space. And based on these predictions, the acquisition function selects another configuration to query F. And after evaluating F on the new point, we collect the results and feed it back to the surrogate model, which updates accordingly. And new predictions are then generated. So this process continues until it reaches a budget limit or a target performance level. And different choices of acquisition function and surrogate models lead to various HPO methods. Okay. For example, by using a Gaussian process as a surrogate model and expected improvements as acquisition function, we create Bayesian optimization. And in the upcoming slides, we'll delve deeper into the components of Bayesian optimization. Okay. In general, the expected improvement aligns with the predictions of the Gaussian process. The Gaussian process value approximates the target function, the F we mentioned, and the point with the highest expected improvements value will be sampled next for the target function. Okay, let's consider a one-dimensional input example. The Gaussian process serves as a regression model here. And unlike linear regression, it produces a Gaussian distribution for each point. So for this point, there's a Gaussian distribution. For this point, there's a Gaussian distribution. Okay, so you can just picture many Gaussian PDFs drawn vertically over the blue curve. And each point on the blue curve represents the mean of the distribution, like those black X here. Those are the means. And the shaded area denotes the variance. So for the evaluated samples, those black X on the blue curve, we have more certainty about their values. So their variance is much smaller than for other points. Also note that points further from, like here, further from evaluated points have a larger variance, indicating greater uncertainty about their values. And in contrast, points close to evaluated samples have smaller variances, and we assume they have similar values to their neighbors. Okay, remember that our goal is an optimization problem, and we want to find a point that maximizes our target function. The acquisition function can either pick a point that's with the highest expected performance based on the Gaussian process, or choose a point with the most uncertainty to learn more about the target function and achieve a better fit. This is known as exploitation and exploration trade-off. In this example, previously evaluated samples provide no useful information for solving max FX. So, for example, this and this point, their expected improvement values are low. Meanwhile, the point near point 3 here offers a good balance between prediction and uncertainty, resulting in the highest expected improvement value. This point will then be sampled and evaluated by the target function. Okay. More formally, the Gaussian process belongs to the genre of non-parametric or kernel methods. It models all sample inputs as a joint Gaussian distribution. To predict the mean and variance of a new sample, the Gaussian process compares its similarity to other samples measured by a kernel. And the Gaussian process also assigns a prior distribution to all the points, and the prediction of a new point depends on both a prior and the evaluation of other points. Okay. So the expected improvement is defined as follows. Here, F star is the value of the best sample so far. Okay. It is a literal expectation of the improvements of the current sample compared to the previous best samples. Okay. And the expected improvements can be further decomposed into two terms, the exploitation term and the exploration term. Okay, let's walk through a single run of Bayesian optimization. Okay, at iteration 1, we fit the Gaussian process with 3 samples, and we get the largest expected improvements at a point near point 3. We then evaluate and fit it into the Gaussian process. And at iteration 2, the uncertainty for all points decreases as addition of 1 point provides more information. Okay. The performance estimation also changes, and we choose 0.7 for the next evaluation. Okay. And finally, after 8 iterations, we end our run and return negative 0.4 here as a global optimal point. Okay, that's all for SMBO and Bayesian optimization. I hope it's clear enough. Please let me know if you have any questions. Otherwise, we'll move on to the random search and grid search. We're good to go?
Yes.
Okay, thank you. in contrast to sequential model-based optimization methods like Bayesian optimization, random search and grid search sample hyperparameter configurations randomly without fitting them to a surrogate model or using any acquisition functions. They simply randomly sample points and wait for the target function to evaluate them. And the results are collected. And when we have a large enough collection, we pick the best one. Okay. And the best part is that they're easy to parallelize. Okay. Bayesian optimization is a sequential optimization method, but there are also optimization methods that are parallel in nature. One such method is CMAES. Okay. It's a population-based algorithm inspired by evolution. It models the search distribution as a normal distribution. And at each iteration, configurations are sampled from the distribution, evaluated for accuracy, and the distribution is updated based on the results. And we call each iteration a generation. To give you an idea of the process, let's say for the first generation, we have 6 configurations here, and we train our model on each of them. Assuming we find that X1, X3, and X4 are the best configurations in this batch, we build a search distribution based on these 3 and sample around them in the next generation. Okay. And in the next generation, we might sample 6 new points. Okay, after evaluating their performance, let's see, X1, X2, X6 are the best, and we'll build a new search distribution over these 3 points and sample from it. And we continue this process until we are satisfied with the results for or reach our budget. Okay. And CMAES estimates the search distribution based on the current population. And each generation has a mean and variance. Okay. The mean update equation is shown here. And it basically updates the mean based on the tried configurations. Okay. It's a weighted sum of the differences between the configuration xk and the previous mean. And the weight here is an indicator of how good the configuration is. If a configuration leads to higher accuracy, we assign it a larger weight, biasing the search distribution towards those examples. Okay, any questions so far for CMAES?
Oh, yes, question. You can shout it or you can come up. They start somewhere, right? They start with something expectation. So first pick at a random, the user you pick about expectation. Doesn't have a big impact let's say the final outcome you choose. For example, very bad. Okay, good question. Yeah, so the question is, these methods are usually sort of iterative, but you have to have an initial condition to start the search. How does the results vary according to how you choose the initial conditions? Xuan, do you want to answer that?
Yeah, sure. That's a very good question. Actually, initialization is very important to get a good HPO results. So basically, it's also like a bottleneck. The result highly depends on the initialization. If we have a good initialization, we can end our HPO search more quickly. Otherwise, it might take longer. Yeah, so it's just an empirical choice. Kevin, you can add more if you want to.
Yes, does that answer your question? So recently, there's sort of a new sub area within hyperparameter optimization. They're trying to do transfer learning. And this is what we do in practice, right? You maybe have experience on a certain task and you know what hyperparameters are good. And when you try a new task, that kind of informs you when you start the search. So there's some new research now on transfer learning for HPO that addresses that initialization problem. Yeah, but it is very important. Good observation. Great. Other questions or comments? How about online? Feel free to drop in the chat. Okay, I think we can go ahead.
Okay, thank you. Cool. Let's move on to another HPO method. So it's PBT, or population-based training. It's another parallel optimization method. And like CMAES, it can be run asynchronously. So the core idea of PBT is to allow the transfer of model parameters. We just talked about transfer learning. Allow the transfer of model parameters and hyperparameters between members of each population. Let's take a look at the differences between sequential optimization, like Bayesian optimization, parallelized random or grid search, and PBT. And so I hope you can get a better understanding of PBT then. Okay, so here in this sub-figure, it shows sequential optimization, like Bayesian optimization. So sequential optimization requires completing multiple training runs, and afterwards, new configurations are selected and the model is retrained from scratch with the new hyperparameters. And this process is inherently sequential, leading to longer optimization times. Okay, and here it shows parallel random search or grid search. And they train multiple models in parallel, hoping that one of the models will be optimized the best. And this approach requires more computational resources to train many models simultaneously. Okay, then it comes to the population-based training. It starts like a parallel search. It first randomly samples hyperparameters, and each training run proceeds asynchronously, and its performance is evaluated periodically. If a model in the population is underperforming, it will exploit the rest of the population by replacing itself with the parameters of a better performing model and modifying the better model's hyperparameters to explore new ones. Okay, so PBT often results in faster learning while using fewer computational resources. This figure shows that compared to grid search, PBT can find better solutions more quickly. Okay. Any questions about PBT?
Questions? Yeah, go ahead. Did you say make the slides bigger?
Make it bigger?
Okay. Yeah. Can you do full screen?
Does it look better?
Is it big? Okay. The lights, that's it. Lights is a good idea. Thank you. Yeah. It's hard to see. Oh, nice. Thank you. Yeah, we changed the dim the lights. Look better in the room now. Okay. Are there questions about this part? Or was there a question there? Now I can't see the audience actually. Do you want to come up or you want me to repeat it? Either is fine. Yes, the question is, are there existing libraries for PBT and other things? The answer is yes. We'll talk about some of them later. But actually, one of our messages here is that it's actually not too hard to implement. So you could do it yourself. And sometimes a harder thing is interfacing that library with your own research pipeline. And so in some cases, it's actually easier just to implement yourself. Yeah, but there are libraries out there, and we'll cover some of the famous ones later. Any other questions or questions online? You have to wave because I can't see. All right, I assume nothing. All right, Xin, do you want to go ahead?
Yeah, sure.
Okay.
Thank you. Okay.
Actually, can you keep it dimmed? I think maybe it was nice. Do you guys like it dimmed or no? Okay, yeah, let's keep it dimmed.
Okay, are we good to go?
Maybe more is fine. Yeah. That's good. All right. Okay, go ahead.
Cool. So far, the HPO methods we've discussed typically require waiting for the model or function f to converge, except for PBT. And this waiting time can be a bottleneck for HPO runs besides initialization, which is why these methods are often called black box HPO. And for us, the target function seems like a black box. However, it turns out we don't always have to train to completion every time. So Dodge 2020 demonstrated that performance early in training is highly correlated with performance later in training. As a result, we can apply multi-fidelity optimization, which uses more affordable approximations of the black box models. For example, we could run fewer training steps before gathering performance results. Okay. One example of multi-fidelity methods is successive halving. It's a prime example, and the concept is pretty straightforward. It assumes that all configurations can be stopped early and aims to allocate the most resources to the most promising configurations. Okay, so just picture this: you have n different configurations and a certain budget, like training time. And in each iteration, as shown in the figure, successive halving returns the top half of the configurations and discards the less effective half. And this process continues until only one configuration remains. And the method wraps up when it reaches its maximum budget. For successive halving, we have two inputs, the budget and the number of configurations. And there's a trade-off between N and B, as they determine the average resources allocated to the configurations. With a larger N, each configuration on average gets a smaller budget. And the training time might be too brief to differentiate between configurations. If N is too small, it means not enough configurations are evaluated. However, in practice, the optimal allocation strategy is uncertain. That's why we have hyperband. Hyperband is just another multi-fidelity method that tackles the trade-off problem, N and B trade-off problem. It's built on successive halving and suggests carrying out successive halving multiple times with different budgets and configuration settings. Let's look at an example hyperband run. We'll define rung, R-U-N-G, not R-U-N, R-U-N-G, rung. We define a rung as a number of cuts we've executed. So in this figure, so this column is a rung here, We can call this rung 0, and this is rung 1. Okay. So each column here represents one successive halving run with a hyperband. For instance, when there are 81 initial configurations, each configuration is allotted one training resource before being cut. Okay, only one of them can run for 81 training periods. And on the other hand, when there are 5 initial configurations, then each can run for 81 training periods. Okay. This figure just demonstrates that hyperband performs better compared to random search. It can accelerate hyperparameter search by 20 times when training resources are limited. Okay, any questions for hyperband and successive halving?
No, okay, we can go.
Good, thank you. So we've explored various HPO methods so far. They can be categorized in several ways: parallel versus sequential, search algorithm versus scheduler, black box, gray box, multi-fidelity. We've discussed evolutionary strategies and PBT as examples of parallel algorithms, while Bayesian optimization represents sequential algorithms, and the best choice depends on your computing setup and specific needs. All these methods operate iteratively and build upon past experiences during an HPO run. There's also a growing research area that investigates, Kevin just mentioned this, meta learning or transfer learning for HPO. This area focuses on determining how past HPO experiences on one problem, domain, or data set can be applied to a new HPO problem. There's a distinction between search algorithms and schedulers as well. Search algorithms like Bayesian optimization and CMAES concentrate on deciding what to sample next. On the other hand, schedulers such as hyperband focus on when to start training a model and when to stop it. This means search algorithms and schedulers can be combined in various ways. So hyperband is actually an early stopping scheduler combined with a random search. Meanwhile, there's another HPO method called BOHB, which blends an early stopping scheduler with Bayesian optimization. Okay. We also have black box methods like Bayesian optimization, which doesn't pick inside the model training process. And in contrast, hyperband monitors and controls the training process, making it an example of gray box methods. Hyperband is also an example of multi-fidelity methods, which basically take advantage of approximations of the real training process or evaluation results. So this can be achieved by limiting training time or training on a smaller subset of data where we get noisy measurements. In this situation, we assume that precise accuracy isn't needed, and instead we want to improve the HPO runtime. Okay. So that wraps up this section. We've gone over the problem formulation of HPO, where the main goal is to find the optimal hyperparameters using fewer searches. And we also explored a variety of representative methods, which can be grouped into different categories. Ultimately, it's up to users, it's up to us, it's up to you to decide which method or methods are best suited for your needs in practice. Okay, that concludes this section for HPO. I will pause here for questions. Okay.
Any questions from the audience? Any questions online? All right. If not, we can move on to the next part. Thanks, Jen.
Okay.
Let me share now.
Oh, sure.
All right. So in this next section, we'll switch gears a little bit to talk about a different. Yeah. Okay. Go ahead. Yeah. Yeah. Go ahead.
I guess some parameters are relatively fixed, like the size of the layers, but sometimes like learning rate. So usually like the techniques like warm-up or something, it's more dynamic. So in that case, what's the relation?
Okay, I see. Yeah. Okay, that's a good question. So the question was, some hyperparameters, you can consider them fixed, right? You try them, it's fixed over the period of your training run. But some hyperparameters are actually kind of dynamic, right? Like some kind of learning rate kind of changes depending on how many training steps you've done. Yeah, so usually what people consider is they don't do this dynamic kind of hyperparameter. So instead you define a fixed hyperparameter that parameterizes this dynamic schedule, right? So you might have a hyperparameter that says, okay, every time my dev loss doesn't improve after n steps, I will halve the learning rate. So those things you can do halving the learning rate, that's a fixed number. And by that you get a dynamic schedule. But that's usually how people do it. I'm not aware of any work that really does changing hyperparameters during search. It sounds like that could be pretty challenging. Yeah, good point. All right, other questions? Okay, good. So now we're gonna switch to neural architecture search. And this is very different from hyperparameter optimization. So for HPO, you can basically, you take your current model, you can apply it. For neural architecture search, there's more work that's involved, but it is a very hot area currently. Okay, so this table tries to categorize the difference between the two. So usually when you talk about HPO, hyperparameter optimization, it can mean any machine learning model. So some people do HPO on random forests, on support vector machines. It doesn't have to be a neural network, right? It can really mean anything. Anything has a hyperparameter, you can do that. Whereas when you talk about neural architecture search, really it's mainly focused on neural nets. And so it focuses on particularities of neural networks to do the search. And second difference is it's pretty obvious. So when we talk about hyperparameters, there are things other than architecture like training pipeline and optimization hyperparameters. But when you're talking about neural architecture search, you're really focusing on the architecture. There's less focus on other things that are not in the architecture. So that is one big difference, and you have to choose what you need. So because of those differences, the kinds of models you might find might be different. Right? So for hyperparameter optimization, you might find a model that says, okay, my best model is say a 4-layer encoder, 3-layer decoder, each has a feed-forward net dimension of 512, right? Something general like that. So it's more coarse-grained. But for neural architecture search, it's usually more fine-grained. Right? You might find something and saying, okay, I have a 4-layer encoder, but the first layer has 5, 12 dimensions. The second layer has different dimension of 10, 12, 24. And the third layer uses 12 as opposed to 8, which is used in the previous layers. So usually neuroarchitecture search focuses on more fine-grained architectural differences. Now, of course, you can encode all of that as hyperparameters, right? You can say, rather than number of dimensions as a single hyperparameter, you can say number of dimensions for layer 1, number of dimensions for layer 2, and so solve neural architecture search with HPO techniques as well. So that's possible too, but it kind of blows up the space. All right, so sort of in summary here, you can consider HPO methods as general techniques that can apply to any method, and it's more coarse-grained, and it can handle, but on the other hand, being coarse-grained, it can handle more diverse kinds of hyperparameters. And neural architecture search, or NAS for short, it's focused on neural nets, and it's very fine-grained, just focusing on architecture. Okay, so that's what we'll talk about here. So here's an example. This is one of the influential work on neural architecture search called the evolve transformer. So they did some kind of evolutionary algorithm, and then they found this complicated new kind of transformer using different blocks. So I'm just showing here, comparing this with a traditional transformer encoder block, and there's some differences. So they got very good scores based on that. Okay, so there are so many papers on NAS now, it's kind of crazy how big the field has become. But I think all of them come down to 3 basic components, and this is a good way to categorize the different methods. So for each method, there's a search space, there's a search strategy, and a performance estimation strategy. And different methods basically differ on how they implement these. So search space, you can imagine this is, you have to define the space of architectures you're willing to search. So for example, here, they were willing to define within a transformer block, they want to search within that block. And they want to put in convolutions or not, put in ReLUs versus some kind of gating. So those are all decisions you make upfront to decide what's the search space. So in a sense, it's a hyperparameter of a hyperparameter problem. Okay, but search space is important, right? Because big search space means you can try many things, but it can also be very slow. Yeah, go ahead. Oh, okay, sure. Can we take off the photo currently? Thank you. Yeah, so, yeah, go ahead. I'm not sure I follow the question. So you're saying when you try a new architecture, yeah. So maybe I'll go through this and then it might be clear afterwards. I think the answer to your question is there are ways to estimate the performance for different hyperparameters, and some are exact, some are heuristic, and so results will be different depending on that. But let's get back to your question after I explain this. Okay. All right. So search strategy is basically you have a search space, and now you're going in this search space. What's the strategy for finding a good solution? And then, like Xuan said earlier, there's this sequential SMBO idea in hyperparameter optimization, and it's very similar here. So you find a new architecture, you use some performance estimation strategy to see how good it is, and then you use that to inform your next architecture, right? So maybe you can imagine what this paper did is maybe they take this traditional transformer, they randomly swapped one of these blocks with something else. So that is the search strategy, decide, okay, which block do I swap? And that gives you a new architecture. And now once you have a new architecture, you try it and get the validation loss. And that's your performance estimation. So based on that, you know, okay, that was a bad idea or a good idea. And then you use that to decide what to search next. Did that answer your question? Oh, I see what I mean. Oh, okay. Yeah, so the question is, when you perform this performance estimate, there are hyperparameters besides architecture hyperparameters that affect the actual loss. And actually I think what's done in the field is people actually just keep those hyperparameters fixed, which is probably not such a good idea. You could imagine running 2 layers of search, right? But that would be expensive. So when you estimate the performance, you actually try different learning rates, for example, right? So because those are things that are not included in the architecture, and you maybe use Bayesian optimization for that. So that is conceivable, but I haven't seen people do that. That's actually a really good point. I mean, that might be a good paper to write about. Yeah, it might be expensive, but it might be really important, right? Because you can imagine when you change the architecture so much, you probably want to change learning rate and other things. Yeah, very good point. Yeah. Okay, so very good questions and comments. All right, so what we'll discuss today is I'll kind of go through a few representative differences. So we'll talk about 2 different kinds of search spaces. One is sequential, one is cell-based. We'll talk about different search strategies. So for the most part, the search strategy is the same as what you have in HPO. So people use the same thing. They use Bayesian optimization. They use evolutionary or things like that. But because these are neural nets, there are new methods that have been developed, and things like gradient-based methods or reinforcement learning methods. I think that's why this field has really grown, is because there's a lot of interesting things you can do here now that you assume you're a neural net architecture. So we'll cover some of that, and that'll be the main part here. And then for performance estimation, the best way to do it is to just fully train your model from scratch, obtain the validation loss. But there are also some ideas on trying to reduce that by sharing weights with previously trained models, or by this kind of one-shot strategy. So I'll cover a little bit of that too. But all those are sort of approximations. All right, so first we'll talk about search space. So search space is basically when you start a method, say you want to optimize a new architecture, you need to tell the model what is the space I want to search. So here's one way to do it, is by a sequence of actions, right? So in this paper down here, it pauses a sequence of actions. First, you decide how many filters you want. Then you decide the filter height, then the filter width, and then the stride. So this is more for vision kind of applications. So you can imagine you keep doing this. So you can say, okay, I want to first decide the architecture for layer 1, filter height, width, stride, etc. And then now you're done with layer 1, and you go to layer 2. And then again, number of filters for layer 2, filter height, and you can keep it going. And maybe there's a stop token that would tell you, okay, no more. And you can view this as a recurrent neural network, right? So the recurrent neural network will predict all these different things. You can imagine these are all the outputs that you predict. And based on this output you predict, you can instantiate a neural net, train it, get its loss, and then use that to update the parameters of this recurrent neural net. And then after you do that, you can again run it through. Okay, so this is one of the first examples of neural architecture search, and this is how they define the search space as a sequence of actions. Okay, does that make sense? All right, so now a totally different way is cell space, search space. And here the idea is that defining by a sequence of actions, you might end up having a very long sequence, and that just gets hard to learn. So there's an observation that really the number of layers is important, but maybe you don't have to have different structure within each layer. So you can just search within a single layer and then just stack them. And you just decide, okay, I'm going to stack 10 of them. It's some kind of fixed parameter, hyperparameter. So in cell-based search methods, they focus on within the layer, which they call a cell, what things to optimize. So there you can get very fine-grained. So for example, here we can say we have for each cell, you can think of cell as a layer, but it can be just a portion of a layer. So you can say for each cell, I'm going to define V nodes, and think of this as computational graphs that's instantiated by some neural net. Right, so you have V nodes. Let's say we have 7 nodes, up to 7 total. And each node can be one of L operations. So for example, you can have a 3x3 convolution, 1x1 convolution, or 3x3 max pooling. Okay, so you can have more if you want to increase your search space, but I just assume we have these 3. And then you also define the edges that connect the nodes, and you assume it's going to be a direct acyclic graph. And that's because we kind of want easy feed-forward propagation. Right, so here's an example. Down here in the corner, we have an in node that represents the input coming from a lower layer, and the output node, and then the remaining 5 nodes here. You can randomly, consider you randomly sample, right? I'll make this a 3x3 convolution. I'll make this a max pooling layer. You can choose whatever you want. And then for each node, you can choose its predecessors, basically choose the input operations that connect to it. And as long as you assume it's a direct acyclic graph, then basically you can represent this kind of structure as an upper triangular matrix, 7x7 upper triangular matrix, right? Where each column and each row represents an element here. And then you have 1 or 0 representing whether there's an arrow, right? And you can imagine changing this matrix, and that will give you different connection structures. Okay, so that's basically one way to view architecture search is you basically define different operations and different connections, and you just let it do whatever connections and operations you want, satisfying this DAG constraint. So this is just an example of kind of the picture here is you can code the picture as some matrix, and basically now you have some representation that you can operate over. So you can imagine when you're doing search, right? If you're trying to sample something nearby, you might change one of these values, or you might change one of the operations. Okay. Any questions here? Okay. All right, so that's the search space. And people have experimented different search space, and it really depends on your application, what you think, what operations do you think are important. So now we'll talk about the next 2 components. Okay, so search strategy, like I said before, you can always just use HPO methods, and that's straightforward. But there are new methods, right? For example, what we mentioned before, with the sequential based search space, then you can have a reinforcement learning based search strategies. And that's very natural to formulate this way. But I'm going to focus on gradient based strategies. So, because these are actually really powerful. And it kind of started with this paper called DARTS. Have people heard of DARTS here? Okay, not really. Okay, so DARTS is very influential in the field of neuroarchitecture search. And basically the idea is that all the search stuff we've talked about, everything is discrete. And in a sense, that's why it's hard. So wouldn't it be nice if we make things continuous? Then we can do gradient stuff. And we know how to do that well. All right, so the idea is here. Remember, we had the cell-based search space. Let's assume that we have 4 nodes and we don't know what's the right connection, right? And the problem of search is finding the right connections and finding the right operations on each of these nodes. So you can imagine, let's just focus on the connections here. So you can imagine defining all possible connections. So here, I'm going to define all possible connections in this DAG. Okay. And then you can just imagine you put weights on each connection. So if you have a high weight, then your data is going to be routed through there. If you have low weight, it's not going to be routed. And if you have 0 weight, basically it means that the structure is defined such that there's no connection there. Right, so it's a very simple idea. So you basically put weights on each of the connections. And because now they're weights, they're continuous values, then you can run gradients on them. And actually, that's the whole idea. And in a sense, it's kind of like, there's many tricks like this, right? Like softmax is in a sense this trick. You want to predict a discrete set of objects, but we don't know how to do that. So we create softmax, which makes it continuous. And in a sense, all this is there's a softmax at each connection. Okay. So the method kind of looks like this. I'll briefly go through this. So don't worry too much about the notation. But just imagine it's a simple 2-liner. And it's kind of impressive, right? You get thousands of citations. It's just these 2 lines. So let's first look at the second line. So we have W here, which are the weights of your neural model. And alpha is basically the weight on the connections. So think of alpha as the softmax weights on the connection. And so what you want to do is, this is a standard training setup, is at the current step, you assume that your alpha weights are fixed. So you have a current set of connections. That's your current network structure. So you do a standard gradient descent to optimize on W, which is your model parameter. So line 2 basically is a standard thing we do. We have a fixed structure, we optimize, find Binder parameters for it. Now, after we do that, we go back and we change the connection weights now. So the next step is we're going to optimize on alpha, and just ignore this part here for now, because you can actually set this to 0. All this saying is you want to change the alpha weights such that you also improve on your validation loss. And you have to do it on a separate data set, because or else these 2 will interfere. Right? So you do it on the validation set. And basically that's it. So imagine what you do is you start out by having every connection being possible. And first you train a model, get all the parameters, and then you gradually basically sharpen the connection weights until finally you have 1 set left. So that's the basic idea. Are there any questions? Does that make sense? Okay, so hopefully it's pretty straightforward. It turns out actually, so there's a lot of follow-up papers on this because it turns out to not be that simple. And one big problem is, yeah. Yeah, the question is, do we have a distribution on each node and also on each edge? And the answer is yes. Yeah, I only talked about edge here. So the question is, if you have a distribution, you can sample, and I think there are methods that do that as well. Yeah. Other questions? Yeah, so I just wanted to mention briefly. So in practice, after being satisfied and finding a set of alpha weights, you usually just take the top and you prune the rest. But it turned out that usually drops the performance quite a lot. So then you have to fine tune again. So there are these little tricks to make sure these kind of methods actually work. All right, so now I'll talk a little bit about a slightly different method. And this is called a supernet or once for all method. And the idea is similar, but there's some, the difference is that this kind of method assumes you have a humongous super network that you train once. And then once you've trained it, you just sample subnetworks from it. And then that subnetwork is basically each sample is basically what you search over. And the idea is that if you can train a super network, then basically most of your work is done. But it's actually a little bit more complicated. So when you train a very big network, I think that maybe I should explain this way. So if you go back here, we're going to train a very big network. And from each network, we're going to sample a substructure. And the assumption of this kind of one-shot method is that it's going to assume that the sampling, after you sample this subnetwork, you do a little bit of fine-tuning on it, and that's sufficient to give you a performance estimate. So that's the assumption. And assuming that's true, then you can pretty much do things very quickly, because fine-tuning is much faster than training from scratch. So whereas the previous method will say, okay, for each architecture, I sample from scratch and going to train from scratch. This one says I'm going to train a humongous model and assume a subnetwork will have similar properties to that. That's actually a big assumption, but people try it. Okay. So how do they ensure that a subnetwork of a supernet is actually similar to the subnetworks trained from scratch? And this is one way to do it. Down here is something called progressive shrinking. So here, the idea kind of follows from network pruning work. So imagine when you're pruning a model, say you train a very big model, but you actually want a smaller model, right? One way to do it is you take out some of the smaller weights, smaller parameters, zero them out, and then you just fine tune on the remaining. And that's a standard method to get prune networks. Now for once for all, what you care about is the supernet, the big network. So what they do is they train the full model, and then when they're training, after a few epochs, they will pretend to shrink it. So they'll pretend to prune it. Maybe they'll take fewer dimensions or take a subnetwork, fine tune it, and then use that gradient update of that small network to update the big network. So this is one way they try to address this assumption that your subnetwork should be similar, should have similar performance when you draw from a big network. Okay. So there's various pros and cons of these. People call this one shot because your performance estimation is very quick. And in a sense, there's always two bottlenecks when you're doing neural architecture search or hyperparameter. One is your search space might be too large, but the main bottleneck is for each model you try to train, it takes a long time, right? So the nice thing about one shot is that this performance estimation is quick. So by making that quick, it means that you can have a larger search space. But the cons of these methods is it's difficult to know that these methods are valid, right? In a sense, you're assuming that the large network and the small network share the same weights, and because they share the same weights, they have similar properties. And actually, there's a lot of empirical results that are mixed in this area. Some are saying this really works, some are saying, hey, it doesn't really work. Another con is that the super network is usually very big. So there's a lot of work in making it fit in memory. But yeah, in general, this is a very popular research area and things are changing really fast. Okay, so to summarize this section, we talked about NAS methods basically being composed of three components. One's the search space, and you can define it as a sequential set of actions, or you can define it as a cell where you just have different node operations and different edge connections. And the cell-based method is actually the mainstream currently. And then we talk about different search strategies. We can use all the HPO search strategies, but there's also new gradient-based strategies now because we're focusing on neural nets. And then finally, performance estimation is sort of tied in with the search, but that's the bottleneck. And if you can do that well, then you can do very good NAS. Okay. All right, any questions? I think that's the end of this section. About any questions online? All right, so now I have a question for you. So we're at 3:35, 10 minutes until coffee. You want to go out earlier to get coffee, or we continue on the next section until we hit the 10-minute mark and then we repeat? Any preference? Who wants to go now? Raise your hand. Who wants to, okay, keep your hand. Okay, who wants to do 10 more minutes? Okay, 2 versus 0. So I guess leaving out wins. Okay, so let's do this. So I think the actual coffee break is 30 minutes total. So we'll basically have a 40-minute break. So come back in 40 minutes. We'll start at 4:15 local time. Okay, 4:15. Yeah, so 40 minutes later. All right, should we get started? All right, so welcome back. So we're gonna change gears now. We talked mostly about machine learning methods. Now we're gonna focus on when you apply this to NLP, what kind of considerations are there? Okay. So first one is multiple objectives. So why is multiple objective important? I mean, it's important in practice. It could depend on your use case, but I think if we really care about deploying our models, you care about decoding time, you care about accuracy, you care about multiple things. And for example, here, this is the same picture I showed you at the beginning of this 700 NeurIPS models. I'm doing a scatter plot of their blue scores and their decoding time. So we really want solutions on the lower right here that are both accurate and fast. But it actually becomes very complicated. How do you find hyperparameters that give you both? Because sometimes they could be very conflicting, right? So So for example, all these hyperparameters here, I can imagine if I increase layer size, I probably increase accuracy, but I probably decrease speed. Right? But there are also some, it's not certain. So number of subword units. If I have small subword units, that means my softmax is small, so probably that increases speed. But that also means my sequence becomes longer. So that could slow things down because transformers are sort of n squared, where n is the number of tokens. Right. So it's not clear how does this hyperparameter interact with speed and accuracy. Right? So and because things are not clear, it's harder to do things by hand, and that's why AutoML could help you. Okay. So I'll just list a couple accuracies, a couple objectives people care about. Right? You could have different kinds of accuracies. You can have inference speed, and inference speed, it can have different kinds, right? Speed on a GPU or on a CPU. Also speed if you're doing things in batch versus one line at a time, that's very different. And also there's a difference between throughput and latency, right? So maybe you care about processing a lot of data. So that's throughput, and you want it to be fast in that sense. Or maybe you're dealing with a real-time application, in which case, when the input comes in, you want to quickly return the output. So that's latency, and that's not necessarily the same as throughput. There's also resource consumption issues, like how much memory do you have? How much disk do you have? If you want to deploy on a cell phone device, for example. And then there's also training resource consumption, and I'm sure we all are familiar with our models not completing and the deadline is coming, right? So training resource is very important as well. So I'm going to make an argument that you could put all of this stuff into hyperparameter optimization and have it do it for you, and that will simplify your life. So really, it really helps for if you're in the deployment setup, but even in the research setup, I think it also helps. So this sort of the ideal case I wish for in the future. In your code, you just say import AutoML tool, define a search space, you define the objectives you care about, and then you just run some multi-objective NAS or something like that. And they'll give you a set of models that fit the best in terms of these multiple objectives. Okay, are there any questions so far? So far, so good. Okay, so now let's step back a bit. So multi-objective is good, but actually, how do you define multiple objectives? And the question of optimality is actually not straightforward if you look at it, right? So say I have two objectives I care about, higher the better. So, and these are a couple of solutions, and they exist in this two-dimensional space, right? So for example, solution F, you can think of this, maybe this is one particular model with one particular hyperparameter. So this one has 0.5 for this objective, 0.1 for this objective. Whereas another one, say this one, let's do this one, right? It has better objective 2, but worse objective 1 compared to this, right? So there are multiple things that are good when you have multiple objectives. So one way to define this is something called Pareto optimal, and I'll motivate that by first defining weakly Pareto optimal. Can I get a show of hands? Do people know about this already? Okay, just a few. Okay, all right. So I'll go over it. It's actually a very simple concept. So we'll define a point here. P is called weakly Pareto optimal if and only if there does not exist another point Q such that all the objectives of Q are strictly better than all the objectives of P. Okay. So in other words, that's saying, okay, I take 2 points. Let's say this is a point P, and does there exist another point such that it's strictly better in objectives? It turns out the answer is yes, right? So there exists A. A has objective 1 is 0.2. That's better than D's 0.1, right? And also objective 2, it has 0.5. That's better than 0.3, right? So A beats B in every single way. Right? So in a sense, we'll say, all right, this point D here is not weakly Pareto optimal. Okay. So basically it amounts to, you pick a point and you kind of look at the upper right-hand quadrant. Does there exist any point in this upper right-hand quadrant? If yes, then you're not weakly Pareto optimal. If no, you are. Right? So for example, point B here is considered weakly Pareto optimal because there's nothing out here that beats it in all objectives. Right? Even though there is a point C here, C is better in one objective, but it's not better in another objective. Right? So we'll say B is weakly Pareto optimal. Okay. Now here you have this case F and C, right? And this is where, because sometimes you can have ties, so that's why there's this definition of weakly Pareto optimal. So we define Pareto optimal in this sense. So a point P is Pareto optimal if only if there does not exist any other point Q such that Q is equal or better in all directions and strictly better in at least one direction. Right. So you can see this is just a simple extension of what we talked about before to handle ties. So what we have here is a point F here is considered weakly Pareto. A point C here is considered weakly Pareto as well as Pareto, which is a stronger condition. Okay. Does that make sense? Questions? All right. So given a set of points, the subset that are Pareto optimal forms what's called a Pareto frontier. And you can imagine Pareto frontier is basically the best set of solutions, right? If I tell you, give me models that optimize both objectives, I would like to see these three models, right? This one is best in one case, this is best in another case. This is actually a good trade-off. But I actually don't want E, right? There's no reason to return E because you know B is better than E. So you can safely ignore that. Okay, so that's a concept of Pareto optimality, and you can use this to define when you have multiple objectives. And that's nice because now we have a framework for dealing with multiple objectives. I won't go through this in detail, but basically the pseudocode is very simple. It's just that if you have n samples, you can imagine this is basically an n-square algorithm, right? To check if a point is Pareto or not, you basically have to look at every single other point, right? So that becomes n squared. And then you have to multiply it by k, for k being the number of objectives. So it's basically order of k times n squared. So it's actually not too large. If you only have two objectives, you can actually do n log n. Yeah, so Pareto is easy to compute. And yeah, that's the main point. All right. Now, once you compute the Pareto frontier, you can actually do something more interesting. So you can first, so given these points, you can compute the Pareto frontier, and then you can throw away the Pareto frontier and then run Pareto again. And then basically that will give you another set of Pareto frontier. So you can have a series of rankings according to Pareto optimality. So sometimes people use this in practice if they want so regression. You can imagine you're kind of peeling an onion. Right? The first layer, throw it away, and you peel again. All right. So that's all good, but often you might wonder, why do I have to do this? You can just, if you have multiple task learning, for example, right? When we have multiple tasks, we always just add them all together and we do gradient on them. What's wrong with that? Well, that is one way to do things, but there are some problems. So for example, say you have m different objectives, you can basically do a linear sum of them to make it one objective, but this will miss some solutions. So here is an example of what happens. So when you're doing a linear combination of objectives, what you're doing is basically you're saying, I'm adding this number with this number. And depending on my weight on this objective, I basically have an array that's going to shift. So if I have my summed objective focusing on objective 1, you can imagine the array is going horizontally, and it will pick out the solution at the max of this array. Now, as you change the linear weights, this array will gradually move upward until it hits this point where it focuses more on objective 2. Okay. Do people see that? Okay. So basically, if you do this kind of linear combination, what you'll find optimal, if you can sweep all single alpha, is F, C, and A, right? So it's a different definition from Pareto optimality. It doesn't get the point B. You can never get the point B because it's actually inside this convex hull. And you always get F, even though it's worse than C. So that's the one demerit of doing linear combination. The other demerit is that you actually have to try all possible weights, which might not be possible. Okay. Yeah, so that's why I prefer Pareto optimality, which is more straightforward. Okay, so now say we have Pareto optimality. How do we actually implement it in one of the HPO or NeurIPS methods we talked about before? It's actually relatively simple. You can do it in a heuristic way, kind of what we're doing here. So for example, Xuan talked about the CMAES method, which is this evolutionary method for HPO. And there's this equation here that says the next sample, you're going to basically sample from the best solutions from the past, right? Now, what you define as best can now be converted to what you define as Pareto. So you can easily incorporate Pareto optimality into this equation and then make it respect multiple objectives. Okay. It's just to give you an example of what kind of results we can get if we just do this simple change. So this is on machine translation. One objective is blue score, and the other objective is time. Okay, and we're running this method, and you can see in the first generation we're here, and then we gradually move, and then the final generation we're getting these points. So this point is better in the Pareto sense compared to this. So since this is a bit randomized, you don't always get the best, but it goes in the right direction. Okay. Any questions? All right. I'll give another example. Say you want to do Bayesian optimization. How do you incorporate multiple objectives in it? And recall when we talked about Bayesian optimization, you have this function that tries to predict, given your search space, what's the predicted accuracy, right? And now you kind of want to predict what's the predicted accuracy times speed, right, in the Pareto sense. So one way to do it is you can plot your points in this two-dimensional space. You can try to think of this as basic calculus, right? You can find first the Pareto frontier, and then given the Pareto frontier, you can try to find the volume of this space. So I'm going to define this red part. That's the volume of these 3 points. And that gives you a single number. And when you sample a different point, for example, in Bayesian optimization, you might predict you will sample this point here. Right? Then you can again compute the area, in the sense of the area under the curve. And the difference here is the expected improvement in 2 dimensions. So that's one way to do it. And again, it's just changing a call within a standard HPO method can let you do multiple objectives. Okay. All right, any questions? All right, so I just want to summarize the section saying, multi-objective is important, and this is, I think, where AutoML will really help if you care about multiple objectives. And Pareto optimality is one way to deal with multiple objectives, and that is easily incorporable into most of the algorithms out there. Okay, are there questions online? All right, then we'll go on to the next section. This is about evaluating. So now, all right, say you're all persuaded and you're gonna try AutoML for your own NLP problems. What kind of things should you think about? Right? Which method should you use? Which method is the best? So that gets an evaluation of AutoML methods. This turns out to be very difficult. So first, I'll give you a brief literature survey of mostly machine learning papers comparing different AutoML methods. And now kind of explain why it's so hard to do rigorous evaluation and propose one way to do it. And finally, I'll talk about the carbon footprint. So I think when you do these kind of big AutoML runs, the carbon footprint could get pretty large. So that's also something to consider in your evaluation. All right. So, all right. So which method is best? Which method should I use? It really is an ill-defined question. I'll survey 4 papers just to give you a sense. Okay. So this is paper 1. So they looked at, and you actually seen this picture before when Xuan presented hyperband. So the way they evaluate is they look at training time and then regret. So regret is the difference between the best possible model and the model you found so far. Okay. So that's one way to do it. And then they argue, okay, this BOHB method works way better. And they got a paper out there. Okay. But that's one way to look at it, is sort of when you're comparing methods based on time. But you should actually look carefully here, right? Is this method actually better? So what this is saying is, if you look at a standard method, like random search. So random search takes a lot of time to gradually decrease the regret. And again, regret is your best found model versus the best possible model. Okay. And then they found that, okay, Bayesian optimization doesn't do much better in the beginning, but if you're given more compute, eventually Bayesian optimization does better. And what they're arguing in this paper is they kind of have the best of both worlds. They can have, if you don't have a lot of compute, their method still does as well. If you have a lot of compute, they still win. Right. So that's one way to view method is, what is your compute budget? Where are you on this curve? And then that might decide which method to use. Now this other paper is interesting. I think the main thing I want to get across here is they tried different methods, HPO methods, on multiple data sets. So each row here is a data set. And then they're showing the accuracy of different methods. So different methods, for example, the blue dot is grid search. The red dot here is the kind of hyperband method. It doesn't matter. But what I want to show is that you see there's a lot of scatter. And one method that might be good here might not be the best here. Right? So in general, there's a lot of variance. And we'll get to this later. Basically, if you review a paper that says on this data set, my method is best, reject it, right? You don't know. Even on multiple data sets, the rankings could change a lot. Okay. This is another example. Maybe I won't go through so much of this. So this other paper, this focuses on computer vision data sets, and they're looking at different neural architecture search methods. And they implemented a lot of the popular methods out there. And they did an interesting experiment where, recall we said each method is composed of an architecture space, the search space, the search strategy, and the performance estimation. And when you write a paper, you actually have all of them, right? And you say your method is better than the other, but you actually might be varying among multiple aspects of them. So what they did in this paper is they held things more fixed. And they found that a lot of the improvements aren't actually due to a method being better, but just due to, say, the search space being better defined for the problem. Right? So definitely any paper you read, take it with a grain of salt, because these systems involve a lot of components. And sometimes when the system does well, it doesn't mean that it's better overall. It might just be one component happened to be better. And then this fourth paper I want to show you. I'm just showing you here for fun. They basically did a literature survey and looked at all the methods. So each row is a neural architecture search method and divided by different kinds of neural architecture search. I'm giving this just to show you how many methods are out there now. And imagine each one of them claims to be the state of the art when it's published. So there's quite a few state of arts in this table. But also one thing to note here is the training time. So people do report your training times. That's good practice. But when you compare things now, right? Say a method here is better on accuracy, but it took way longer to train, then actually it's very hard to compare these methods. Okay. All right. So I went through this pretty fast, but I think the main thing I want to show is that evaluation is not easy. Results out there are pretty mixed, and don't trust any single paper that says they're always the best. Okay. All right. So why is HPO and NAS hard to evaluate? And basically, there's a fundamental limitation is we want to do HPO because it takes time to do it. You want to save time, right? So by definition, it takes a long time to train a model. So of course, if you want to run an HPO algorithm that trains, say, 100 models, that's 100 times the amount of budget, right? So basically, it's very hard to run experiments, right? So let's say, and this is very common. So I propose a method. It takes me a week to train a model. I have, say, 100 GPUs, so I trained for a week. I got some results, right? But then I actually want to run some baselines, but I don't have that much budget left, right? So that's sort of why it's so hard. So here's a paper that really put it very bluntly. So this is 2019, and this is sort of when the field started. So it says of the 12 papers published since 2018 at NeurIPS, ICML, and ICLR, none are exactly reproducible. And there's another paper recently that kind of says the same thing. It's just really hard to compare. Everyone has their own grid. And of course, now there's no 12 papers. It's more like several hundreds papers. And none of them are reproducible. Yeah. So I kind of painted a very grim image of this field. So what can we do? Here's one solution. And so this is sort of what we did when we went into this field for trying to do it for NLP. So it's called tabular benchmarks. And the idea is you basically run grid search or random search over your data set. And you kind of do a one-time fixed cost. You try every single thing you can think of. And then you just save all the results. Right, so basically here I'm saying I have X is the different hyperparameters, f of X is, say, the accuracy of each of those models. So I just put them in a table and put it on GitHub, right? So then now for some kind of HPO algorithm researcher, that person can basically not train models anymore, but basically look up from the table. And that makes it much faster to do HPO experiments to look at which method is better. And once you know which method is better, then you can apply it to your real data set. So it's a very simple idea. The disadvantage, of course, is that this one-time fixed cost may be very large, right? So you're going to burn a lot of compute trying to do a big search. And second is your models are now fixed. So when you run HPO, you're only sampling from this fixed finite universe. So there might be things outside of this. So that's a disadvantage. But I think if you're interested in trying different HPO methods and you're not sure if for your problem which method works best, this is one way to do it, is you do this one-time fixed cost. Okay, so here's an example of what we did for NeurIPS, just to make things more concrete. So we tried different data sets, Chinese to English, Russian to English, on different domains like TED, WMT. And for each of them, we basically did a grid search. And these are the kinds of hyperparameters and the potential values. So we try to do as much as we can. And now it's in a table. So whenever someone proposes a new HPO method, they can just query this table and see how it works. So the nice thing about this is now since everything is sort of simulation, you can run a lot of experiments, right? So this experiment I'm showing different curves are different kinds of HPO methods. The actual method doesn't matter, but we can also plot error bars now. So we can run the simulation multiple times. Like there was a question earlier, how does initialization matter? Now we can test that. So we can try with different initialization and see how different the results are, and we can plot the variance. So this will help you do better benchmarking. Yeah, I think that's all I want to say. We also did multi-objective, but that's not important. Are there any questions here? Yeah, go ahead. Can you repeat the last part? How do you take into account what? So you're saying simple models scale better? Yeah. Scale meaning in what sense of scale? Scaling to more data? Okay, I see what you mean. Yeah, that's a good point. So I think, say, in a world where we can figure out what's the best architecture, and then that's it, we always just use the same architecture, then we actually don't need AutoML. But we're in this world where, depending on your data set size, depending on your data set characteristics, the best architecture could differ. And like you said, some architectures might scale better than others. Right, so that's why we need AutoML, we know that our default is not the best in every single case. Now, in terms of the actual question of scaling, there is this problem of, for example, when I'm training this, some of these are very different sizes of data. So the best model here on the TED Talks data is not the best model on the WMT data set. And that's totally natural. And that's actually good, right? That's why this kind of research will help uncover which models scale better. Yeah. Did I answer? Yeah. Go ahead. Yeah. Yeah, so question is, in neural architecture search, can you add constraints to bias to simpler models? Definitely you can do that. I actually haven't seen many papers doing that. I feel like this idea of multi-objective is still pretty new. So I mean, that could be an interesting research direction on how to do it, but I think it's doable. Yeah. Right. Other questions or comments? Yeah, go ahead.
So in your set, do you check them? But that's what this costs. Slightly different method.
Yeah.
If I how that, then what do you think might
Yeah, that's a great question. So question is, if I say I make this data set, but if I have another metric that I discover later I want to use during deployment, and I don't really know if it correlates well with my current metric, what do I do? That's kind of tough, I think. And that's why it's hard. It was very hard to design this data set because we were trying to anticipate what we would need. For example, when we did this, blue was pretty standard, but then quickly Comet became very popular in evaluation of MT, right? So that is one disadvantage of these tabular benchmarks is a static benchmark. So once you've done it, that's it. I can imagine there might be ways where maybe you could view it as a transfer learning kind of thing, except now your evaluation data is kind of out of domain. So there might be some way to formulate it. I have to think about it a bit more. Yeah. Actually, I guess in some cases, if you kept enough of the logs, you could recompute some things. So it might not be a lost cause. Yeah, but it depends on the metric. Yeah. All right, good points. Any other questions? Yeah, go ahead.
Setting like you are training a language, so you have a fixed budget or floats.
Yeah.
So you can decide to use a large model, but use less data, or use a relatively small data, use more data, relatively small model, but more data for training. So is your current framework in the optimal this case?
Yeah. So question is, say you have a fixed budget, and you can either have training on big data, but maybe a smaller model, and or training on smaller subset of the data, but bigger model.
Yes.
And what's the right trade-off? And can these things deal with it? And the answer is yes. So you can view the data subset as a kind of approximation. So you can say, if I train on the full data set and estimate its performance, that's my true performance. But if I train on part of it, that is the approximation of the true performance. Right? So you can frame it that way, and then you can mix, and you can probably use a Bayesian approach as well. So there are ways to deal with that. Yeah, that's a good observation. Yeah, go ahead. Yeah, so tabular benchmarks, so have people adopted tabular benchmarks? The answer is yes. We actually didn't invent it. There was another work also doing tabular benchmarks on computer vision data sets. Good question. Are there such benchmarks for text classification? I'm actually not aware. I think I found one archive paper, but it was very sparsely written, so I wouldn't recommend it. I actually haven't seen much in the text world. Yeah. Actually, one thing that would be a great outcome of this meeting is if people have different models, different data sets they're interested in, and if we can work together on creating new benchmarks, that might be interesting. Because I've only done machine translation benchmarks. And actually one of the questions we often get is, but I want a different task. How would this transfer? Yeah, so if there's any call for collaboration, definitely welcome. Okay, yeah, this is very good. So I'll just briefly mention this competition we ran at the first AutoML conference. So we tried to, there are these competitions out now. And I think they're running a second conference pretty soon. So feel free to check out the website, automl.cc. But for example, we took our data set here and then we basically ran a public competition. And these are some things that people found. And this is great because we kind of encourage the machine learning folks to work on our problems because they've been working on these small data sets for so long. And for the bigger data sets, it's always computer vision. So it was very good that we got some participation here. So for example, one team had the approach using evolution methods, and they used basically a decision tree kind of ranker for fitting the surrogate model. And that was kind of interesting, it's kind of different. There's another team, they use something called tree structure parson estimator. And then they focus on transfer learning. So they basically took our, say, Chinese data set, learned the best parameters and tried to transfer it to our Japanese data set. Yeah, so basically I think this could be an interesting area to be in. And we're interested in trying their approaches for our data sets. All right, now you can actually go beyond tabular benchmarks. So the same group that tried, this other group that tried tabular benchmarks, they tried something else where they actually just created a new model that estimates the accuracy. And so now you can think of, now you have a tabular benchmark where you can generate infinite many new rows in the table. Now the question here is actually, will this introduce bias, right? Because now it's not a real accuracy anymore, and you're using this as an evaluation data set. So personally, I'm not convinced about it, but just wanted to mention that such ideas are out there. Yeah, and this is a paper to check out if you're interested. They were trying to show in these plots that their generated rows are correlated, well correlated with true results. All right, any questions so far? Okay, so now switch gears a bit and talk about carbon footprint. So you can imagine AutoML is basically trading human effort with compute time, right? So we're trading human effort. So we should also think about what's the computer effort, right? What's the cost of it? So looking at energy costs and carbon footprint, I think is important going forward. And AutoML has both good and bad potential impacts, right? You can run AutoML in a crazy way in which you cause a lot of carbon footprints. But you can also run a responsibility, and that actually saves you compute compared to a very exhaustive search. Okay, so first I'm going to talk about two papers, and they're kind of conflicting against each other. And I should say that I'm not an expert in energy estimation, so I actually don't know the true answer, but just to give you a sense of things to think about. So this paper up here by Struble et al., it was pretty influential. So it tried to estimate carbon footprint. I should say it's called CO2e. So that means carbon dioxide equivalent. So you could have nitrogen gases and other things. So people convert it all to the same unit called CO2e, right? So they had this table in the paper saying, okay, the amount of carbon dioxide equivalent generated by air travel by one person between New York and San Francisco is about 2,000 pounds. And a standard NLP pipeline like parsing or training a parsing might take this much, but a transformer might take about 200, right? So that's not insignificant compared to this 2,000 number. Yeah. But even more, they say, okay, using neural architecture search, you have this crazy large number. And this is a very scary number, right? So this paper got a lot of attention. And I think it was good that it brought people's attention to the consequences of our training runs. Okay. Now I should explain more then. How do you actually calculate carbon footprint? Actually, are there experts here? Do people know? Okay. So I had to look this up and I'm not totally confident myself, but roughly, just as a rule of thumb, you can think of it this way. So first of all, you need to think about your power consumption. So that's called as PT, okay? That's your power consumption from training a model, and it's sort of in the unit of kilowatt hours, okay? And how much power do you spend? It depends on the power used by your CPU and the power used by your RAM and the power used by your GPU times G. Here's the number of GPUs, okay? So that's the power used by each of your compute units, okay? And then multiply T to get, T is time here, because you need to know how long you've used this. And then power usage effectiveness. So this is a number, think of each 1 watt of compute in your data center to crunch some data might require some overhead because you need to cool the computer with a fan, right? So this power usage effectiveness is a constant you multiply to estimate for that. And usually this is not trivial. So good data centers have low numbers close to 1. And that's sort of the secret of good data centers. How can they push down this PUE? Okay. And this division is just make a kilowatts. So this is how much power your model has consumed during training. And then you need to think, okay, from this amount of power, actually how much CO2 would it have generated, right? And another constant is here, but this constant differs depending on your case, right? If you're using renewable energy, this constant will be smaller. If you're using coal, it will be larger, right? So this constant depends on a lot of factors. And then finally, you get this number, right? So I think if you're trying to do power estimation, there are tools now that give you this a little bit, but it's not, I don't know how accurate it is, but you will also need to find out what these constants are, which could not be possible. Like for my academic compute grid, I don't know what's my PUE. I don't know even how to find out. But basically that's how you compute these numbers. Are there any questions? Okay, so yeah, so this paper goes on. So this paper uses some formulas and tries to estimate the amount of CO2 equivalents that's been generated by these different models during training. Now I should mention now a second paper came along by Patterson et al. And they were basically a rebuttal against the first paper. And they're saying that it's actually challenging to estimate the carbon footprint retrospectively, because you don't know when when the authors trained these models, what was its PUE? What was the electrical usage, right? So, so a lot of things, constants that you use could be difficult. So what they did is, so they're from Google, so they had their internal measurements, and they noted that what they believe their carbon footprint for their NAS algorithm is down here. So it's actually around 7,000 pounds. Okay, so just converting to pounds here. Okay, so basically you have one paper that's saying their NAS method costs 7,000 pounds of carbon dioxide, and then another method saying 600,000. So that's a big difference, right? So I would kind of leave it there. There's been a lot of back and forth, and you can find out more if you're interested. But I just mainly want to raise awareness that it's important to think about carbon emissions if you're doing these kind of big search, but also it's not straightforward to estimate actually how much you're using. So you have to be a bit careful. Okay. All right, any questions? About online? Okay, all right, so to summarize this section, evaluation is very difficult. First, if you want to evaluate, you just think about what do you care about most? Do you care about fixed budget case, or do you care about more general case? And what metrics, what data sets do you care about? And second, if you want to do a really rigorous evaluation, I would suggest doing some kind of tabular example if you can afford it. Yeah, okay. So now we'll switch to toolkits. Xuan, can you share your slides now?
Sure.
Yeah, so now say you're sold and you want to try this at home. What are the options? So Xuan will talk about different toolkits that you can use.
Okay. In this section, we'll dive into the AutoML software implementation. And we'll start by introducing some existing AutoML toolkits, and then move on to a case study of a software solution we have developed ourselves. I hope this will give you an rough idea of how easy it is to integrate AutoML into your own workflow. Okay. HPO or NeurIPS algorithms are generally straightforward to implement. The real challenge lies in interacting with AutoML algorithms and underlying computing infrastructure. When designing AutoML software, one needs to consider their specific computing environments and how to automatically submit jobs, check job status, evaluate and collect results, parallelize tasks, and maximize GPU utilization. And at the same time, the software should be flexible enough to allow users to customize their AutoML runs by specifying arguments such as the number of GPUs, the number of configurations to try, and the number of epochs for each run. Okay. Google Vizier and Retune are two examples of existing AutoML toolkits. So Google Vizier is a managed service that applies black box optimization for Google's own internal hyperparameter tuning. It's built to handle large-scale experiments and is very flexible to deal with multi-objective optimization. And Retune is scalable and user-friendly library for hyperparameter tuning. It supports a bunch of optimization algorithms and parallelization strategies and plays nicely with popular machine learning frameworks. Both of these tools are solid choices for researchers to dive into AutoML. There are also other available choices. You can do a little bit survey before you just choose one. Okay. We want to say it's actually not trivial to hesitate on the decision whether to use existing AutoML toolkits or implement your own. If you go for existing AutoML toolkits, you might have to rework your entire training pipeline. But if you already got a solid training pipeline, like Amazon Sakai for machine translation, and you are not too keen on messing with it, you might consider creating an AutoML wrapper instead. Okay. And as we'll demonstrate shortly, this second option is actually quite doable and might be the perfect solution for your needs. Now let's dive into a case study where we create an HPO wrapper for Amazon Sakai. So Amazon Sakai is an open source sequence-to-sequence framework for neural machine translation built on PyTorch. And Kevin developed this Sakai recipes, which consist of training scripts and recipes specifically designed for the Sakai toolkit. You can find these Sakai recipes with AutoML support on GitHub. In this case study, we implemented an automatic hyperparameter search using asynchronous successive halving on top of Sakai recipes. Let's first discuss the HPO method we employed, the asynchronous successive halving, or ASHA for short. ASHA is an asynchronous version of the multi-fidelity HPO method successive halving. And after introducing ASHA, we'll dive into our software design and present a practical use case to give you a better understanding. Okay. If you recall from earlier in the talk, we mentioned successive halving, which is a multi-armed bandit algorithm. This algorithm employs early stopping to terminate jobs that don't show much promise, allowing limited computing resources to be focused on more promising tasks. Okay, and so recall that we call the period between two cuts a run. So this could be RUNG. This is run 0. This is run 1. Okay, this is a very important term to remember before we introduce the ASHA. Okay. So in the sequential successive halving, the algorithm waits for all configurations in a run to complete before promoting any of them to the next run. ASHA, on the other hand, removes this bottleneck by allowing asynchronous promotions. So the idea here is to promote a configuration to the next run when there's an idle worker or when a configuration has already secured a position in the next run. And this approach ensures parallelization with optimal GPU utilization. That's why we chose to use ASHA. Okay. Here's an example showing how ASHA works. Let's assume we want to find the optimal configuration from 10 different configurations. Okay, and we decide to set the promotion rate to 1/2, meaning that when it's time to make a decision, we'll cut half of the jobs and let the other half run for a longer duration. So at run 0, we have 10 configurations. Suppose that at this point, 6 of them, the red ones, 6 of them have reached the points where they're waiting for a decision to be cut or not. And since the number 6 is greater than 5, which is half of 10, we can be sure that the top one from these 6 configurations has secured a position in the next run. Okay, in this case, configuration 8 has the highest blue score so far, so we promote it to the next run. Okay. On the other hand, if we were to apply sequential successive halving in this scenario, we would need to wait for all the 10 configurations to finish running at run 0 before promoting any configuration to run 1. If there's a straggler, it would result in wasted computing time. And Asha, however, addresses this issue effectively and enables more efficient use of GPU resources. Okay, moving forward, we have here 7 finished jobs out of 10 at run 0. So we can promote another configuration to the next run. In this case, it's configuration 1, as it has second highest blue score among all. Okay, let's assume that after some time, we reach the following states from run 0 to run 1, as we've shown before. We can promote configuration 4, and at the same time at run 1, there are 3 finished jobs, and since 3 is greater than half of 5, we can promote the top 1 configuration from these 3 configurations, which happens to be configuration 8 in this instance. Okay. To help clarify the process, let's take a look at the pseudocode together. So first, users can specify the configuration, search space, and some other arguments, such as the frequency of checking each job state, the minimum and maximum training time for each job, the duration of training within each run, and the promotion or reduction rate, and the total number of available GPUs. Okay, and in each time step, we check the state of each configuration and submit jobs to idle GPUs. And then first we check the state of each configurations and take appropriate action based on their current state. Next, we identify configuration candidates eligible for promotion to the next run and initiate training jobs. To be more specific, job state can be classified as converged, diverged, running, maybe, and finished training. Here is success, or experiencing various errors which are not uncommon, such as GPU errors and memory errors. Is there a question there?
No.
Okay, and we detect these different states and respond accordingly, either by recovering the job or terminating the job or removing the configuration entirely. So when idle GPUs are available, we identify configurations ready to advance to the next run. And the promote function here selects 1 configuration from all the candidates. It can be implemented using either random search or Bayesian optimization. And finally, we submit a train job and let it run for a specified period of time. Okay, so this is a checklist of how we dealt with some of the implementation challenges. How to get the job state. We get a job state by checking the job log, and how to automatically check the job state. We set up a timer running in a background thread, and how to interact with a grid or GPU cluster. We check the GPU states, and during development, we debug carefully with possible errors. How to deal with failed jobs. We either resubmit or delete them. Okay. So we've been using the Asha implementation for our own real experiments, and it turns out very useful and easy to use. Here we show kind of a why example run on our grid at Johns Hopkins. So we only need to run a single line of command here, sh submit run AutoML.sh. And of course, you need to set up some arguments beforehand. Then we can just sit back or go work on other stuff and wait for the program to run and finish by itself. And here it prints out the arguments we set beforehand. We set the minimum number of a checkpoint for each job to 1, and the number of checkpoints within each run also to 1, and the maximum checkpoints to 6, the reduction rate to 2, and total number of available GPUs to 4. Okay, and this example is optimizing blue, which is a single objective optimization. It's also capable of doing multi-objective optimization, such as optimizing blue and, for instance, decoding speed at the same time. And here our search space consists of 10 hyperparameter configurations. Okay, and at run 1, we start with 10 configurations, and the program autonomously determines which candidates should be promoted to run 1, and we submit the train job to the grade. Okay. As a remember before we set up a background timer, and as a background timer, which is a pre-specified interval, the program checks the status of submitted jobs. In this example, configurations 1 and 7 have completed training and now undergoing evaluations on the validation set, while configurations 6 and 3 are still in the training process. And to keep users informed, the program also displays a list of finished jobs. Okay. Here it shows that Asha finished successfully, and it prints out the pruning process. We got the best configuration here 6 and the best blue 8.3. Okay, so this is the end of this section. Please let me know if you have any questions. Otherwise, I'll hand the mic to Kevin.
Yeah. Any questions for Shen? The code is on GitHub. You can check it out if you're interested. And like we said, there are existing toolkits you can use as well. But hopefully you see from this demonstration that Shen had that it's actually not too difficult to design one for yourself. So depending on your use case, if you have questions, feel free to reach out. Okay. All right, so now let's move on to the final section. All right, so this final section, I'll just do a brief survey of HPO and NAS methods that's been published in the NLP literature, just to give you a sense. I actually won't cover all of them for time reasons. So I'll just cover a few and feel free to refer to the slides later on your own. Okay. So this is one of the first papers I found on HPO for NLP. So Yoga Tama et al. Looked at different hyperparameters on input text features. So things like, this is back in the days, pre-neural days actually. So you want to decide what are stop words, what words above some frequency counts you include as features. And they're just doing some kind of logistic regression classifier on top of those features. So these are the hyperparameters they've tried, different kinds of, in a sense, preprocessing hyperparameters and also some optimization hyperparameters, and got reasonable results. And they use a Bayesian optimization method to do this. And the follow-up work by Xuan et al. Is something similar, but they focus on training on subsets of data, and that refers to a question earlier that can you estimate your performance on not on the full training set but on the subset. So this is what they did. They ran Bayesian optimization but on subsets, and found that that could increase the speed of the overall HPO method. By the way, if you're interested in more details, just raise your hand and I'm happy to talk more. But I just want to give a flavor of things that have been done in our field. Okay, so this paper by Beck et al. Looked at statistical machine translation. And this is back in the days when we had a Moses decoder, and you care about things like beam size, how much pruning you do during that, because that affects the speed of your decoding. I think this problem is still relevant today, right? In our standard transformer, the beam size does matter in your speed. Actually, if you do a beam size of 1, you can actually save a lot of compute, right? You don't even need softmax anymore, and that can go very fast. But once you go up to beam sizes 2, then you start incurring costs. So basically, this is a multi-objective problem, right? You want speed, but you also want accuracy. And it's hard to tune because these are sort of discrete things. So what they did was they applied Bayesian optimization. They tried some parameters, hyperparameters, like these are old hyperparameters that we care about back in the days. But just think of different pruning hyperparameters during beam search. So they try different hyperparameters, look at the speed and accuracy, and then run Bayesian optimization. And the idea is that you don't need to do a big grid search. You can pretty quickly find a reasonable model. Right. Now, this is a paper by Zhang et al. Looking at HPO for knowledge graphs. So these are things like I have a graph and the nodes and edges are being embedded as vectors, and they could be used for various applications like knowledge-based completion or link prediction. Now, there are apparently many hyperparameters you can think of when you're doing this. So when you're training a method on this graph, you usually want to sample, and you can think of how many negative samples do you want, and that really affects the results. What loss function do you use? What regularizer to use? What's the optimization? So all these are actually optimizer style hyperparameters, nothing related to architecture, but these people found that it's worth it to actually do a smart search over this. And they showed that that could give them better results. One interesting thing they tried also in the paper is they've run their HPO on a smaller graph and kind of adapted those results on the full large graph. In their case, it worked out. But that is some kind of design decision you need to make when you're running your own HPO, is do you use your full data set or not? Actually, any questions so far? All right. This paper by Liu and Wang, relatively recent, looked at HPO for fine-tuning of hyperparameters. And this, I think this is getting more relevant to our recent age of this pre-training fine-tuning paradigm, right? So they looked at this Electra model, kind of like a BERT model, right? And they're going to fine-tune it on their specific task. Now, when you fine-tune something, these are various optimization hyperparameters that might matter. So, so basically, they looked at random search, they looked at ASHA actually, and Bayesian optimization, and have some interesting results. Okay. So I think when you think about this day and age, even if you're given a large pre-trained model, if you want to fine tune it, that is potentially a hyperparameter search problem as well. Okay. Okay, now we're going to move from HPO to NAS. So this paper by Wang et al., I really recommend reading it if you're interested in NAS. So they looked at this once for all NAS architecture applied to transformers. So recall NAS basically lets you, the gradient version lets you sort of, the super network with gradient version is you're training one big model and then you sample subnetworks, right? So basically what they have here is they have a humongous transformer model. And then when they sample subnetworks, they basically sample subsets of their hidden dimensions. So for example, this is encoder layer 1. They have heads and the feed-forward network, and they basically can cut out a portion of it. And they take strict subsets here so that the assumption of sort of different size models being related is more relevant. Right, so they basically try different versions of this hidden dimension, try different versions of this embedding dimension. And then they run a evolutionary search on top of it and show that they can actually find pretty good models for different kinds of hardwares. All right. This next paper is an improvement on the previous paper. And it's saying that, okay, when you're trying to estimate performance, you can do it better. And they use a ranking method to estimate performance. So the idea is you don't need to know exactly this model has this accuracy. You just need to know that this model is better than this other model. So maybe we can estimate the ranking performance easier than the actual performance. So this next one is on text classification. So imagine you have you have a sentence pair, and you run some LSTM or BERT on top of it, and then you have a final multi-class classification on top. Right, so that's pretty standard in our world, and they tried different ways. So this is from Nuru and Bansal, and they basically did a search on the cells and found some interesting different cells you could use. However, this follow-up work by McLaughlin et al. Sort of expanded on the previous paper and showed that it didn't always work, and the results were more nuanced. Okay, so I think that's something to bear in mind when you're doing these kind of experiments, is since it's hard to evaluate, you could have mixed results like this. Okay. I think maybe that's enough to talk about. I don't want to feel like this is the end of a long conference. I don't want to make people stay too long. All right, so basically, there's a few other works. If you're interested, feel free to check these out. Okay. All right, any questions on that part or anything before? Oh, go ahead.
Curious about the once for all NAS.
Yeah.
What's the overheads in order to find a better model?
Okay, what's the overhead for once for all NAS? That's a good question. So first of all, the idea is you train a super network and then you subsample subnetworks and then fine tune those a little bit. And then you evaluate the performance of the subnetworks and use that in the sort of architecture search framework. So the first cost is when you train this humongous big network. There's a time cost and there's also a memory cost. So that could be, I think that is probably the biggest overhead there. The subsampling and the fine tuning, I think the overhead is much smaller there in general. Yeah. Mm-hmm. Good. Other questions? Okay, so I think I'll summarize everything today and maybe let you out a little bit earlier. So first of all, so these are all the things we talked about today. First of all, we tried to motivate why it's important to think about hyperparameters. I showed this graph where we see that we train many different models on the same data set. the histogram of their accuracy, it has a large variance. And so people often just present the best one, but you might not be so lucky to find the best one. All right, so it's very important to tune hyperparameters. And then later we talked about different hyperparameter optimization algorithms. These are the main ones you can think of. Simple ones are grid search, random search. The Bayesian optimization is very popular. The Bayesian optimization is sequential, so it might fit well if you have fewer compute devices. But if you have more compute devices, maybe you want something parallel to try multiple models at once. So those are models like this, like population-based training or evolutionary search. Now, on one side, you have what's called black box methods. These are basically methods that train to completion, and you don't really care what's inside that black box. You just want to evaluate the performance at the end. But this can be expensive to train stuff to completion. So the multi-fidelity methods kind of peers into this black box and say, hey, can we stop training runs early? Can we take different approximations of the performance, such as training on smaller data sets? And we talked about successive halving there. And I think this is very important algorithm that if you want to try this, I would recommend successive, the asynchronous version, Asha, that we talked about. It's probably the most effective if you just want to do it on the parallel system. Yeah, and we also discussed there's a distinction between search and scheduler, where search is what sample do you pick next in your search, but scheduler is sort of how much do you train something, and scheduling the actual training process, and that's different. Okay. Next, we talk about neural architecture search, and as I said, there's many papers now in this field, but you can roughly group them by these three aspects. So what kind of search space do they use? And this is very important because that determines the best possible thing they can find. And then we talked about search strategy in particular, because these things focus on neural nets. You have very interesting new gradient-based strategies that you can exploit. So things like darts and once for all NAST, those are really interesting. And then finally, when you sample some architecture, how do you estimate the performance? You can train from scratch, or maybe there's some shortcuts with some assumptions, and that's also a big area of research. Okay. Then we switch gears to talk about when you actually want to use this in, say, an NLP application. We said multi-objectives are important. It's very complex, but it's actually not too hard to incorporate Pareto optimality into any of the methods we talked about before. So it's totally doable. And I think that will be one of the biggest values of AutoML is this multi-objective aspect. And we talked about evaluation is very hard because it takes a long time to train. Have their benchmark is one way to deal with it. And then last but not least, we talked about choices of toolkits or doing it your own. It really depends on whether you already have an existing training pipeline that's easy to modify or whether you just want to wrap around. Okay, and then finally we did a survey. So that's basically it. Any final questions or comments? Yeah, go ahead. I was worried you would ask that. All right, so what do I think about architecture search in the context of large language models? So I think that is an important problem. So if those people building large language models, I'm sure they care about these things and they must be doing some kind of intelligence search, but it could be done manually. I think maybe they have many smart engineers who just kind of by experience learned how to do this. And in a sense, AutoML is trying to extract that kind of human experience and do things automatically. Yeah, so I think my response is AutoML is important if you want to train. No, I should not say this the other way. So hyperparameter tuning is important, definitely when you're training a large language model. And it's even more important, right? Because you really can't afford trying too many hyperparameters. But whether you do it using AutoML tools or whether you just rely on a very good engineer, I think that's a separate question. And probably at this time, you will rely on a good engineer, I think. Yeah. Oh, okay, that's interesting. So you're talking about, what about in context learning? Actually, that's a good point. So when for all these AutoML methods, you always have a metric defined. So say I'm doing MT and I say, okay, I clear about blue score. Then I just optimize on that, right? So I could have multiple scores, right? So say I do a large language model, I can say I want to optimize super glue benchmark. I want to optimize this other QA benchmark or this MT benchmark. But when you want to do in context learning, I guess you want to do more, right? You want to do tasks that hasn't been out there before. And I actually don't know what is a metric we can use to define such a thing. So maybe it won't work in that case. Yeah. Yeah, that's a very good question, I think. Thank you. Oh, go ahead. Yeah, do you want to use the mic to answer? I think this will be interesting.
To answer with his question, I think in the first keynote by Edward Refensat, he talked a little bit about this, about what metrics during training of large language models to use as a proxy for their in-context learning performance. And he was talking about, I think, just perplexity, and that there were some studies that showed that the perplexity correlates well with downstream in-context learning performance. So I guess a little bit to answer his question, a good idea now is to find some proxy metric during training that correlates better with this in-context learning performance.
Yeah, that's a good point. But I guess we can do it for perplexity, but then later with the instruction fine-tuning and other kinds of things, it's less clear what to do, I think. Or maybe that part doesn't matter. We focus on architecture search on the first stage. Yeah, that could be possible.
Sure,
yeah.
Just to remind something that they said in the first keynote.
Yeah.
Actually,
yeah.
Not
Yeah,
sure.
that's a good way to end the day, is to refer back to the first talk. Thank you. Okay. Other questions or comments? All right, then I think we'll end here. Thank you all so much for coming. And if you're interested in more, I'm always happy to talk. Just shoot Xuan and I an email. Okay. Thank you.